Welcome to the Deep Dive. We're the show that takes a whole stack of sources and boils them down to the key insights, giving you that expert level understanding. Today, we're plunging into a topic that's, well, it's everywhere: generative AI. When most of us think about it, we picture ChatGPT, maybe DALL-E, creating images, these incredible outputs that honestly feel a bit like magic. It seems like this technology just burst onto the scene, changing everything. But our mission for you today is to cut through that hype. We're going on a deep dive to really pull back the curtain on generative AI. We'll explore its hidden roots in probability, look at some surprising, maybe even worrying, flaws in the data it uses, and touch on the truly groundbreaking frontiers opening up right now. Our goal: to shortcut your way to being genuinely well-informed, getting you insights that, frankly, even many experts are just now starting to fully grasp.
That's a great way to put it. And what's fascinating, is that the magic we see today isn't really some bolt from the blue. It's actually deeply rooted in, well, decades of statistical theory. We're talking over 50 years of history here. As we unpack that foundation, we'll also uncover why the very data that fuels these systems, well, it's creating a bit of a looming crisis. Issues of quality, bias, even the scary idea of model collapse. And maybe most importantly, we'll see why the future AI isn't just about making models bigger and bigger. It's probably going to involve entirely new ways of thinking about how AI learns and works.
Yeah.
So yeah, get ready for hopefully a few aha moments that might really reshape how you see AI.
Deconstructing the engine, the overlooked probabilistic foundations.
Okay, excellent framing. So
Mhm.
to really get a handle on systems like GPT, we need to rewind a bit, right? Long before this recent deep learning boom, it might feel like GPT just materialized, but generative AI isn't some sudden invention, not at all. It's more like the culmination of, 50 plus years of work?
Mhm.
Statistical modeling, probability theory. It's a long journey.
Exactly, a journey through half a century of really foundational work. And across that whole history, there's this one core idea that keeps popping up. The fundamental goal for all generative models is to learn a probability distribution from data.
Okay, learn how the data is distributed.
Right. And once the model understands that distribution, it can then sample from it. It can generate totally new synthetic data points that look like the original data it learned from.
So that's the thread connecting everything,
Yeah.
from early algorithms to today's big LLMs.
That's the one. It connects algorithms from the 1950s right up to today's generative pre-trained transformers, the GPTs everyone talks about. So it's less about a massive paradigm shift, and more about incredible refinement and, frankly, massive scaling of that core principle.
Okay, that makes sense. It builds on itself.
And that brings us to a really crucial distinction. It's something that often gets blurred in, popular discussions, but it's key to understanding why generative models do what they do. I'm talking about the difference between generative and discriminative AI.
Right. I've heard those terms.
It's not just academic jargon. It's the core reason why something like GPT can write a poem, or DALL-E can make a picture. While a simpler model, trained on the exact same data, might only be able to tell you if a piece of text is a poem.
Okay, so what's the difference then? Discriminative first.
Sure. Discriminative models, their main job is learning the boundary between different classes of data. Think of them like classifiers. Their goal is to figure out the probability of a label Y given some observation X, PYX.
Like, is this email spam or not spam?
Exactly. Logistic regression, support vector machines, those are classic examples. They map input features directly to a label, they discriminate between categories, but they don't really need to understand how the data itself was generated.
Okay, they just find the dividing line.
Precisely. Now, generative models, they're much more ambitious. They aim to learn the full joint probability distribution of the data, PXY. They build a whole statistical model of how the data was created in the first place. It's like learning the recipe, not just tasting the cake.
So they ask, what process likely created this data?
That's a good way to think about it. Which category is most likely to have generated the signal I'm seeing? Now, because they have this deep model, they can be used for classification too, using Bayes' rule. But the defining thing, the really crucial part, is their ability to generate new data points. By sampling from that learned distribution, PX, they can create brand new stuff that's statistically similar to the training data. They understand the underlying structure.
That distinction really does clarify a lot. So learning the structure lets them create. And you mentioned earlier models.
Yeah.
What's a good early example of this generative idea?
A great classic one is naive Bayes. Many people know it as a classifier, often for spam filtering, like you said. But its underlying mechanism is fundamentally generative, even though its main use became classification.
Okay, how does that work? It uses Bayes' theorem, right?
Exactly. Built right on Bayes' theorem, which is all about updating beliefs with new evidence. In classification, it lets us calculate py, the probability of class u given features x. The generative part is how it learns. It learns two key things from the training data. Pxy, the likelihood how probable are these features given this class, and py, the prior how common is this class overall.
Right, likelihood and prior. And the naive part.
The naive part comes from a very strong simplifying assumption it makes. It assumes conditional independence among features, meaning, given the class way, it assumes each feature is totally independent of every other feature.
Which probably isn't true in reality most of the time.
Almost never completely true, no, that's why it's naive. But it makes the math way simpler. But the key insight for us is its generative story, the hypothetical process it assumes. It's like the model first picks a class based on the prior py. Then for that class, it generates values for each feature independently based on the likelihoods it learned.
I see. So it has a little recipe, pick a category, then sprinkle in features associated with it.
Exactly, and you see this in different flavors, like Gaussian naive Bayes if the features are continuous numbers, or multinomial naive Bayes for counts, like word counts in text documents. So even in something as common as a spam filter, you've got this foundational generative concept. The AI is learning how data gets created, not just what it is.
That's fascinating. Learning the recipe, not just identifying the dish, but that naive independence assumption. That sounds pretty limiting for complex stuff.
It absolutely can be. Real-world data rarely has features that are perfectly independent, and that's where Gaussian mixture models, or GMMs, come in as a significant step up. GMMs tackle that limitation head-on. They model the data not as coming from a single simple distribution, but as a mixture of multiple Gaussian distributions, those familiar bell curves.
So instead of one bell curve, it's like several overlapping ones.
Precisely. Imagine your data has distinct subgroups or clusters. A GMM assumes each data point comes from one of k different Gaussian components, each with its own mean, average, and covariance spread. The probability of any single data point is then a weighted sum of its probabilities under each of these k Gaussians.
So the model has to learn how many components, what each one looks like, and how much weight each one gets.
Exactly. It needs to learn the mixing coefficients, the weights, k, the means, and the covariance matrices for each of the k components. The tricky part is learning these parameters when you don't know beforehand which data point belongs to which component. That's usually where the expectation maximization, or EM algorithm, comes in.
EM algorithm. Okay, how does that work, roughly?
It's an iterative process. In the E-step expectation, it calculates the probability, or responsibility, that each data point belongs to each Gaussian component given the current parameters. Then, in the M-step maximization, it uses these responsibilities to update the parameters, the weights, means, and covariances to better fit the data. It goes back and forth, E-step, M-step, until the parameters stabilize.
Okay, it refines its guess iteratively.
Yeah.
And once it's learned those parameters, how does it generate data?
The generative process is quite elegant then. First, it chooses one of the k components to generate from, based on the learned mixing coefficients, the CFACs. Then it simply generates a data point by sampling from that specific Gaussian distribution, and this ability to model data as a composite, a mixture of simpler distributions, that was a really foundational concept. It directly foreshadows how modern deep generative models work. If you think of one Gaussian as a simple recipe, GMMs are like having a whole cookbook and knowing which recipe to use when.
That cookbook analogy is great. Okay, so GMMs handle complex distributions. But what about data where the order matters, like text or speech?
Right, exactly. So far, we've mostly talked about data points treated independently. But for sequences, speech, text, time series data, the order is everything. And that's where hidden Markov models, or HMMs, became incredibly important. They were one of the first really successful generative models specifically designed for sequential data.
Hidden Markov models. Okay, what's the core idea there?
The core idea is a system with underlying states that are hidden. You can't observe them directly. These hidden states evolve over time following a Markov process, and crucially, each hidden state has a probability of emitting an observable output or symbol.
Can you give an example?
Sure. Imagine someone is in another room flipping coins, but you only hear the result heads or tails. You don't know if they're using a fair coin or a biased one. The hidden state could be using fair coin or using biased coin. The observable outputs are heads and tails. You try to infer the hidden state sequence based on the observed sequence of flips.
Okay, that makes sense. So what defines an HMM? What are its parameters?
There are three key sets of probabilities you need to define an HMM. First, the initial state probabilities, often called what's the chance of starting in each possible hidden state. Second, the transition probabilities, A. Given you're in one hidden state, what's the chance of moving to any other hidden state in the next time step? This uses the Markov assumption the next state only depends on the current state. And third, the emission probabilities, B. Given you're in a particular hidden state, what's the chance of observing a specific output symbol?
Got it. Initial state, transitions between states, and emissions from states.
Yeah.
How does it generate a sequence then?
The generative process follows those probabilities directly. You first choose an initial hidden state based on the initial probabilities. Then from that state S1, you emit an observation O1 based on its emission probabilities B. Next, you transition to a new hidden state S2 based on the transition probabilities A from S1. Then you emit O2 from S2, transition to S3, and so on. You just repeat the emission and transition steps.
And this was used for things like speech recognition.
Hugely influential there. The hidden states might represent phonemes, basic sound units, and the observations would be features extracted from the acoustic signal. Also used in bioinformatics for things like gene sequencing, HMMs really showed us how AI could learn to generate coherent sequences, how to tell a story, probabilistically. You can definitely see a direct line from HMMs to how today's big language models string words together.
Absolutely. And this whole journey we've just traced from naive Bayes through GMMs to HMMs and even looking ahead to modern deep learning. There's a powerful unifying principle underneath it all. It's not just a random walk through different ideas. It's a clear intellectual lineage.
Okay, what's the connecting thread?
The core thread is maximum likelihood estimation, or MLE. It's the fundamental optimization principle that connects all these models. The goal of MLE, simply put, is to find the set of model parameters that makes the observed training data as probable as possible. Maximize the likelihood of seeing the data you saw, given the model. So whether it's counting frequencies like in naive Bayes, or using that iterative EM algorithm for GMMs.
Or using sophisticated gradient-based optimization like in deep neural networks today. The underlying goal is MLE. Find the parameters that best explain the data.
That's a really unifying idea. And you mentioned dependency modeling. How did that evolve along this path?
That's a fascinating way to look at the history, too. Naive Bayes started with the most extreme simplification. Assume all features are conditionally independent given the class. Total independence. HMMs took a huge step by modeling local first-order sequential dependencies. The next thing depends only on the current thing. Then things like recurrent neural networks, RNNs, and LSTMs came along. They used complex hidden states to try and capture longer-range dependencies, reaching further back in the sequence. And finally, the transformer architecture with its self-attention mechanism broke that linear chain entirely. It allows every part of the sequence to directly look at every other part. It models global, non-local dependencies.
Wow. So from total independence to local dependence to trying for longer range and finally to global dependence.
Exactly. It's a clear progression in how sophisticated the dependency modeling became. Modern deep learning is, in many ways, a massively scaled engineering solution to that same core statistical problem HMMs and others were tackling decades ago. But this massive scale, this ability to model complex global dependencies, it also raises a critical question. What happens when that sheer scale introduces entirely new kinds of problems? Problems perhaps related to the data itself.
The data dilemma curation, contamination, and the specter of model collapse.
That's the perfect pivot. We've gone deep into the engine, the probabilistic heart of generative AI. Now let's talk about its fuel, the data. And you hear this all the time, right? More data, better AI. Simple. But as we're about to find out, it's really not that simple at all. The data itself is turning out to be a hidden battleground. It shapes everything. Performance, bias. It's arguably the most critical and maybe the most problematic part of modern Gen AI. That more is better mantra. It hides a really complex reality, curation choices, hidden biases, systemic vulnerabilities. The data isn't just fuel, it's deeply influencing the engine's design and behavior.
Couldn't agree more. The performance, the character, everything about a large language model is just inextricably tied to what went into its training data.
Yeah.
And looking at how these massive text data sets have evolved, it reveals really different philosophies about how to build them, each with major downstream effects.
Okay, so where does this data come from? What's the starting point?
Well, often the starting point is something called the common crawl. You could think of it as this primordial soup of the internet. It's a massive, publicly available archive, petabytes of raw web data scraped from billions and billions of pages. It's huge, but it's also messy, unfiltered. Contains everything, high-quality text, junk HTML, ads, nonsense, harmful stuff.
Right, the raw, wild internet, so someone had to clean that up.
Exactly. That led to datasets like C4, the colossal clean-crawled corpus developed by Google. Their philosophy was aggressive filtering. They took one big snapshot of Common Crawl and applied a bunch of rules heuristics to try and clean it up. Removed duplicates, boilerplate, non-English text, aiming for reasonably clean and natural English text. Ended up around 750 gigabytes. And C4 became foundational for models like T5, and later Meta's Llama used it too.
But was it actually clean? Did the filtering work perfectly?
Well, no. Later audits found significant problems. Despite the cleaning, C4 still contained a substantial amount of problematic content, pornographic, biased, offensive material, even stuff from white supremacist sites. And maybe even more worryingly, the specific filtering rules they used ended up disproportionately excluding content from certain marginalized groups like LGBT plus communities, Black authors, Hispanic authors. So the curation itself, the choices made in filtering, inadvertently baked in certain biases and excluded voices.
Wow. That's a clear example of curation choices having unintended consequences. Was there an alternative approach?
Yes, a different philosophy emerged with the pile, created by Eleuther AI. Instead of just filtering one giant web scrape, the pile aimed for curated diversity. It's a bit larger, around 886 gigabytes, but it's explicitly composed of 22 distinct sub-datasets. They intentionally included things like PubMed Central, medical abstracts, ArcSIF, scientific preprints, GitHub Code, Books 3, a large book corpus, Stack Exchange, Q&A.
So aiming for broader knowledge, especially technical stuff.
Exactly. And a key aspect was differential weighting. During training, they intentionally gave more weight, more training epochs, to data sets they considered higher quality, like academic papers and Wikipedia, to really drill in that cross-domain knowledge. Importantly, they were also much more transparent about the contents, documenting known biases, profanity levels, and even consent issues within the various subdatasets.
Okay, so filtering versus curated diversity. Any other major approaches?
More recently, the team behind the Falcon models introduced refined web. They sort of went back to the Common Crawl idea, but with much more sophisticated and stringent cleaning. Really aggressive URL filtering, advanced text extraction techniques, massive deduplication efforts. They ended up with a huge data set, 5 trillion tokens derived purely from web data, but heavily filtered. And the surprising outcome: models trained only on this highly refined web data actually outperform models trained on curated mixtures like the pile.
That is surprising, so maybe super careful filtering of web data is enough.
It raises interesting questions. But the key takeaway across all these is that these curation choices are not neutral. They are a powerful, often invisible form of editorial control. They embed the creator's values, priorities, and biases right into the foundation of the model. C4's heuristics marginalize certain voices. The pile explicitly prioritized academic content. Refined Web's filtering rules likely have their own subtle effects. It's basically algorithmic governance happening right at the data creation stage, shaping the AI's worldview before anyone even starts fine-tuning it.
That's a really powerful point, the invisible hand of data curation. Now, beyond those big decisions about what data to include, you mentioned another threat, data contamination. What's that about?
Right. This is another really significant and maybe underappreciated threat to how we evaluate these models. Data contamination happens when data from the benchmark evaluation sets the test we use to measure how good a model is accidentally gets included in the massive training data sets.
Wait, the 10 questions end up in the study material?
Exactly. Many standard benchmarks, things like MMLU for general knowledge, GSM-8K for math problems, Truthful QA for factual accuracy, they're often publicly available, maybe on GitHub or websites. So when companies scrape the web for training data, they can inadvertently hoover up these benchmark data sets too.
Oh, I see. That completely breaks the test, doesn't it?
It fundamentally compromises the whole evaluation process. It turns what should be a test of reasoning and generalization into just a test of memorization. The model might score really high not because it's smart, but just because it saw the exact question and answer during training.
So the scores we see on leaderboards might be inflated.
They absolutely can be.
Yeah.
It leads to artificial performance inflation, giving us this misleadingly rosy picture of AI capabilities. The benchmarks lose their diagnostic power. They can't tell us what the model really knows or where it struggles. And you can't fairly compare models if they have different levels of contamination. It messes up the whole competitive landscape.
Has anyone actually studied how bad this effect is?
Yes. There was a really insightful large-scale study specifically on machine translation models. The researchers deliberately contaminated the training data and measured the impact. They found that when both the source text, say English, and the target text, say French, from a benchmark were included in training, it caused massive inflation in BLEU scores, the standard metric. We're talking increases of up to 30 BLEU points for an 8 billion parameter model. That's huge. a completely misleading jump in perceived quality.
30 points. Wow. Did scale matter?
Yes, interestingly, the larger 8B model was 2.5 times more sensitive to contamination than a smaller 1B model. Scale amplified the memorization effect. They also found that partial contamination, just seeing the question but not the answer, for example, had a much smaller impact. The model really needs to memorize a whole input-output pair. And how the contamination was distributed mattered too. A big chunk all at once caused a temporary score spike, while sprinkling it throughout had a more persistent effect. And logically, it only really helps if the model already has some basic grasp of the language involved.
This really makes you question things. Are we systematically overestimating how fast AI is progressing? Could the state of the art be partly an illusion built on memorization?
It's a very real concern. And researchers are trying to figure out how to fix the benchmarks to resist this, but it reveals this fundamental tension, a trade-off between fidelity and resistance.
Fidelity and resistance. Okay, explain those.
Fidelity is how well the modified benchmark still measures the original capability you cared about.
Mhm.
Does changing the test change what you're testing? Resistance is how well the modified benchmark resists being memorized by a contaminated model. Does the change stop the model from cheating?
And there's a trade-off.
Absolutely. Think about ways to modify a benchmark question. You can do semantic preserving, single changes, swap a synonym, add a typo. Small changes, these have high fidelity, they test the same thing, but low resistance. A contaminated model easily sees through them. Okay, what if you stack multiple small changes, that's semantic preserving, combined? Now you get maybe medium resistance, but the fidelity starts to drop. You might be subtly changing the task itself. And then you have semantic altering approaches, like using another LLM to generate brand new paraphrase questions. These have high resistance, the model hasn't seen them. But low fidelity, you're fundamentally changing the test.
So the better you are at stopping memorization, the more you change what you're actually measuring.
Precisely. It's
Correct.
a tough nut to crack. Just paraphrasing existing questions probably isn't enough in the long run. This strongly suggests that we need truly dynamic benchmarks, maybe with continuous streams of brand new, unseen evaluation data to really be sure we're testing reasoning, not just recall.
So we have data curation issues, benchmark contamination. It feels like the data itself is a minefield. And you mentioned another long-term threat, model collapse. That sounds ominous.
It does, doesn't it? And it's a potentially very serious, insidious threat, also known as the generative AI feedback loop. Think about it. The internet is rapidly filling up with content generated by AI. Text, images, code. What happens when the next generation of LLMs are trained on web scrapes that include all the synthetic data produced by their predecessors?
They start learning from AI-generated stuff, not just human stuff.
Exactly. You get this self-referential training loop.
Yep.
And research suggests this is really bad news. As models are trained on increasing amounts of synthetic data, they start to forget the original true distribution of human-generated data. Their understanding of the world becomes like an echo of their own past generations, getting progressively distorted.
What are the consequences of that?
Several things. A progressive degradation of quality, the outputs might become blander, less diverse, more statistically average. A loss of diversity, the model converges on its own stereotypical patterns, losing touch with the richness of human expression. And critically, an amplification of biases and errors. Any flaws in the early models get repeated and potentially magnified by later generations learning from them.
And model collapse is the extreme version.
Yes, that's the extreme case where the model effectively forgets the true underlying data distribution almost entirely. Performance plummets, utility drops off a cliff. The implication is pretty stark. We might be facing an existential threat where the very data commons we need to train AI gets polluted by the technology itself. It's been compared to digital inbreeding, leading to a loss of genetic diversity in our information ecosystem.
The fragile giant's unseen limitations and the breakdown of scaling paradigms.
Digital inbreeding. Wow, that's a powerful image. And connecting that back, this idea that the system can degrade itself really challenges that narrative of smooth, inevitable progress, doesn't it?
It absolutely does. This relentless push for just bigger models, more data, more compute. It's often presented as this guaranteed path to ever greater capability. But it hides a surprising brittleness. Even these incredibly advanced models have structural limits, hidden failure modes, those scaling laws we hear about. They aren't unbreakable laws of physics. We're starting to hit some fundamental walls, revealing a fragility in these systems we often think of as almost superhuman.
That's fascinating, this idea of fragility in the giants. Can you give an example of such a limitation?
A classic, and still very relevant, one is catastrophic forgetting, also called catastrophic interference. It's a really striking phenomenon. Imagine if every time you learn something new, like a new language, you completely forgot your native tongue.
Okay, that would be bad.
Yeah. Right. That's basically catastrophic forgetting for an AI. It's not a gradual fading of knowledge. It's often a sudden, drastic loss of previously learned abilities when the model is trained on new information. So take a model trained to tell cats from dogs. If you then fine-tune it only on recognizing different breeds of dogs, it might completely lose its ability to identify a cat. Poof, gone.
Why does that happen?
It boils down to how neural networks store knowledge. It's distributed across all those connections, the weights. When the model learns a new task, it has to update those weights. If the new task requires changing weights that were crucial for an old task, that old knowledge gets overwritten, lost.
So it's a fundamental conflict between learning new things and retaining old things.
Exactly. It's called the stability-plasticity dilemma. A learning system needs to be plastic enough to acquire new knowledge, but stable enough to retain the old. Humans are remarkably good at this balancing act. Current neural networks, not so much. They really struggle.
And the practical consequences are huge, I imagine.
Definitely. It severely limits the idea of continuous learning for things like robots operating in the real world or AI assistants that need to constantly adapt. And for these giant foundation models, retraining them from scratch every time you have new data, including all the old data, that's incredibly expensive, computationally prohibitive.
Are people working on fixing this?
Oh, yes. It's a major research area. There are various mitigation techniques. Some use regularization methods like elastic weight consolidation, EWC, which tries to identify important weights for old tasks and penalize changes to them. Others use rehearsal or replay, basically, storing some old data and mixing it in with the new data during training. But that costs storage and compute time. There are also architectural solutions, like progressive neural networks, which freeze the old network parts and add new neurons specifically for the new task, and even some brain-inspired methods trying to mimic things like memory consolidation during sleep.
It really highlights a fundamental difference in how AI learns versus how we learn. That stability plasticity thing is key.
It is. And related to that, this idea that just scaling up more parameters, more data will solve everything, that's also hitting a wall. We've seen these empirical scaling laws, right? Predictable improvements with more resources. The Chinchilla paper famously showed optimal ratios of model size and data. But recent theoretical work, particularly from researchers like Coveney and Suchi, argues pretty strongly that scaling alone cannot get us to scientific-grade reliability.
A scaling wall, why not? What's the argument?
They make a few key points. First, look at the actual scaling exponents, how much improvement you get for a given increase in resources. They're typically tiny, less than 0.1. What that means in practice is, to reduce the error rate by, say, a factor of 10, you might need 10 to the power of 10, or even 10 to the power of 20 times more compute. You hit severely diminishing returns very quickly. Brute force scaling just becomes physically and economically impossible beyond a certain point.
Okay, diminishing returns. What else?
Second, they point out that the very thing that makes these models powerful, their ability to generate complex, non-Gaussian outputs, is also a source of fragility. Non-Gaussian processes are prone to errors that pile up in unexpected ways, leading to what they call fat-tailed error distributions. Rare but extreme errors become more likely. This can cause information catastrophes, where the model's outputs just become incoherent.
So the complexity cuts both ways.
Exactly. And third, think about these massive data sets scraped from the internet. As the dataset size grows, the number of purely coincidental, spurious correlations grows exponentially. Eventually, this flood of meaningless correlations can overwhelm the true, meaningful signals in the data. So paradoxically, adding more data can actually make it harder for the model to learn reliably. It exacerbates the noise problem.
More data can make things worse. That's counterintuitive.
It really is. And this theoretical wall is hitting a practical wall, too. Data exhaustion. We might simply be running out of unique, high-quality text data to train these models on. The supply isn't infinite. Even if you try to get around that by training for multiple epochs, passes through the same data, you still hit diminishing returns and dramatically increase the risk of just overfitting and memorizing the training set.
So the brute force scaling party might be ending.
It raises that question very seriously. Are we hitting fundamental limits here? It strongly suggests we might need to redirect efforts towards more efficient architectures or different learning paradigms, not just bigger versions of the same thing.
That makes sense. And another area where bigger isn't automatically better seems to be this idea of long context windows. Models boast about handling 100,000 tokens, even 1 million tokens, implying they can read and understand whole books. But is that really true?
Yeah, that's often what's being called the long context mirage. While the models can technically ingest very long sequences, their ability to effectively use and reason about information spread across that entire context, well, the evidence suggests it's often quite limited.
Why is that? What breaks down?
Two main things. First, that quadratic complexity of self-attention we mentioned earlier, ON2, it just gets computationally brutal for very long sequences. But second, even if you can afford the computation, there's an issue of informational dilution. The attention mechanism has to spread its focus across potentially hundreds of thousands of tokens. It gets harder and harder to pinpoint the truly critical pieces of information in that sea of text. The attention gets spread thin.
And this leads to that lost in the middle problem.
Exactly. Researchers have done these needle in a haystack tests. You hide a key piece of information somewhere in a very long document and ask the model to retrieve it. What they consistently find is a U-shaped performance curve. The model is pretty good if the needle is right at the beginning or right at the very end of the document. But if the crucial information is buried somewhere in the middle, performance drops significantly.
So it's like it only really pays attention to the start and the end.
Largely, yes. Some studies suggest models might only be effectively using maybe 10–20% of the context they're given, effectively ignoring large chunks in the middle. So you feed it an entire novel, but it might just be skimming the first chapter and the last chapter, potentially missing the crucial plot twist halfway through. It's like having this huge desk, but only ever looking at the stuff piled up on the corners.
That's a major limitation if you want genuine document understanding.
It is. And all these issues, catastrophic forgetting, scaling limits, the long context mirage, they contribute to what some researchers are calling cognitive failure modes. These are situations where LLMs fail in ways that look superficially like human cognitive biases, but the underlying reasons are quite different.
Cognitive failure modes, like what?
So, researchers are designing clever prompts to test this. For example, models show a framing effect. If you start a prompt with some irrelevant code, say a Python function that happens to end with return false, the LLM might nonsensically include return false in its own generated code, even if it makes no sense for the actual task. The framing influenced it.
Okay, that's weird. What else?
Anchoring. If you include an example solution in the prompt, even if it's flawed, the model might anchor on that flawed example and incorporate parts of it into its own answer. Or the availability heuristic. Models often default to the most common version of a problem they saw in training, even if you explicitly ask for a rarer variant. Ask for the square of sums, x plus y2, and it might still give you the more common sum of squares by 2 plus y2.
So it falls back on familiar patterns, even when told otherwise.
Exactly. And they struggle with causal reasoning, too. They often rely on simple shortcuts, like assuming temporal order means causation. And they heavily rely on their pre-trained parametric knowledge, the stuff baked in during training. If the prompt gives information that contradicts this stored knowledge, the model might just ignore the prompt and go with what it knows.
These aren't just random bugs, then. They
Right.
point to something deeper.
That's the argument. They're symptoms of a core architectural issue. The knowledge in these models is essentially static, frozen after training. It's not adaptive. A transformer can't dynamically allocate more thinking power to a hard part of a problem. It can't easily overcome the scaling limits we discussed. It struggles to prioritize information in real time within that long context window. This leads to this strange paradox. They have superhuman memory for facts seen in training, but subhuman reliability and robustness when faced with novelty or complexity. It reveals a profound lack of deep, abstract understanding.
The emergence debate. A genuine phenomenon or a statistical mirage?
That paradox is really striking: superhuman memory, subhuman reliability. And it leads us right into one of the most fascinating and maybe slightly unnerving debates happening in AI right now. Emergence, emergent abilities. The idea here, as I understand it, is that just by making models bigger, completely new capabilities can suddenly appear, things the smaller models just couldn't do, popping up unpredictably.
That's the core claim, yes.
But others say maybe it's not real. Maybe it's some kind of illusion. The implications here feel huge, right? For what AI could become, the risks, how predictable it is. This feels like a really important debate to unpack.
It absolutely is. The stakes are very high. The case for genuine emergence usually rests on two key properties people observe. First, sharpness. You see this dramatic, almost instantaneous jump from the model performing at near random chance on a task to suddenly performing at a very high level. Second, unpredictability. You supposedly can't predict these leaps just by looking at how smaller models perform. The improvement curve isn't smooth. There's a sudden, unexpected takeoff.
And where did people see this happening?
A lot of the initial evidence came from observing models like the GPT-3 family, and also from large-scale benchmark evaluations like Big Bench. Researchers noticed that for many complex tasks, smaller models would just flounder, get near zero scores. But then once the model crossed a certain threshold in scale, more parameters, more data, more training compute boom, performance would jump dramatically.
Like what kind of tasks?
A classic example often cited is multi-digit arithmetic. One study showed a model going from basically guessing on three-digit addition to getting over 80% accuracy almost overnight as it scaled up. And you couldn't predict that 80% from the near-zero performance of the smaller versions. Similar sharp jumps were reported for things like answering college-level exam questions, generating working code, program synthesis, understanding subtle idioms.
So it's not just getting slightly better at things, it's like unlocking entirely new skills.
That's the claim, qualitative shifts, not just quantitative improvements, doing entirely new things. And the AI safety implication is pretty stark if this is true. If dangerous capabilities like advanced deception, manipulation, finding security exploits could just emerge suddenly and without warning at some future scale, well, trying to proactively align or control AI becomes incredibly difficult. This view suggests a fundamental uncertainty about what future larger models might be capable of. That makes risk assessment and governance really challenging. It is a genuinely unsettling thought for safety professionals.
Okay, that's a powerful case for emergence and why it matters for safety. But you said there's a counter-argument, a skeptical view.
Yes, there's a very compelling skeptical take put forward most prominently by researchers at Stanford. Their core argument is that these apparent emergent abilities aren't a fundamental property of the models changing drastically. Instead, they're an artifact of the metrics we use to measure them.
An artifact of the metrics. How so?
They argue that if you look at the model's underlying capability, something smoother, like its ability to predict the next token accurately, its loss function, that capability usually does improve smoothly and predictably with scale, just like the scaling laws suggest. However, many of the benchmarks used to test for emergence rely on nonlinear or discontinuous metrics. Think about multiple choice questions. You get 0 points until you pick the exactly correct answer. Then you get full points. Or checking if generated code compiles. It's either yes or no, all or nothing.
Right, those are sharp thresholds.
Exactly.
Yeah.
So the skeptical argument is the emergent leap we see happens simply when the model's smoothly improving internal capability crosses the sharp threshold imposed by that harsh all-or-nothing metric. The model was getting steadily better all along, but our measuring stick only registered the improvement once it crossed that specific line.
Did they demonstrate this?
Yes, quite effectively. They went back to tasks where emergence had been claimed, like that arithmetic example. Instead of using exact match accuracy, which is all or nothing, they used a more continuous metric like token edit distance, basically, giving partial credit for answers that are numerically close but not exactly right. And when they did that, the sharp emergent jump in performance disappeared. Instead, they saw smooth, continuous, predictable improvement as the model scaled up.
Wow. So changing the ruler changed the shape of the growth curve.
Precisely. It strongly suggests that, at least in some cases, the magic might just be an illusion created by our choice of measurement. Like saying a kid suddenly learns to ride a bike the moment they can stay up for 60 seconds, ignoring the weeks of wobbly progress beforehand.
That's a very compelling counter-argument. So where does that leave the debate? Is it settled? Is emergence just a metric illusion?
It's definitely not settled. It's a really active area of research, and the truth is likely nuanced. There are valid points on both sides. While the metric artifact explanation is powerful and explains a lot, it might not be the whole story for every claimed emergent ability.
Why not?
Well, some researchers have pointed to examples where emergent-like jumps seem to persist even when using continuous metrics. That French to English translation example using BLEU scores, which gives partial credit, sometimes gets cited. Also, you could argue that for certain really complex multi-step tasks, maybe there is a genuine threshold of capability required. Maybe the model needs multiple underlying skills to develop and coordinate before it can even begin to solve the task correctly. In that case, you might still see a sharp phase transition in performance, even with a continuous metric, just because the task itself has a non-linear difficulty.
Okay, so task complexity could play a role. Any other angles?
Another perspective is that what looks like emergence might actually be the models getting much better at in-context learning as they scale up, meaning they become much more adept at understanding and utilizing the examples or instructions given in the prompt itself rather than developing fundamentally new abstract reasoning abilities. The capability was latent, and scale unlocked the ability to use the prompt effectively.
So it's learning how to learn from the prompt better.
Kinda, yeah. And philosophically, this whole debate echoes much older arguments in science about reductionism versus emergence in complex systems. Think P.W. Anderson's famous More is Different essay. Do genuinely new properties arise at higher levels of complexity, or can everything be reduced to the behavior of the components?
It's a deep question.
It really is. But regardless of who turns out to be ultimately right about emergence in LLMs, the debate itself highlights something critical. Our current methods for evaluating these powerful models are fragile. They can lead to radically different conclusions depending on how you measure things. If emergence is real, it means our predictive models of AI progress are incomplete, and we face serious safety challenges. If it's mostly a mirage caused by metrics, then our evaluation tools are misleading us. Either way, it points to a kind of methodological crisis. It undermines our ability to confidently understand AI progress and prepare adequately for its future.
Peering into the black box, the frontier of mechanistic interpretability.
That fragility in evaluation is a really sobering thought. It makes you wonder just how much we actually understand about why these models do what they do. Which brings us neatly to the next big challenge, the infamous black box problem. So imagine having a genius surgeon, incredibly skilled, but they literally cannot explain why they made each incision, why they chose this technique over that one.
That's a great analogy.
That's kind of where we are with a lot of AI. As these models get bigger and more complex, their internal workings, their decision-making processes become incredibly opaque. For a while, maybe people accepted this as the price of performance, a necessary trade-off. But that view is changing fast, isn't it? Especially as we deploy AI in really high-stakes areas, medicine, finance, science.
Absolutely. It's becoming untenable.
We need to know why. Interpretability feels like it's becoming a major bottleneck. For safety, for fairness, for trust, for reliability, we need to understand the why.
You're spot on. And the quest for interpretability isn't monolithic. It exists on a spectrum, with different approaches offering different levels of insight. At one end, you have what are sometimes called inherently interpretable models or glass box models.
That's fact.
Yeah, things like decision trees or sparse linear models or maybe generalized additive models. Their advantage is transparency. They're designed so that an expert can look at the model structure and understand exactly how inputs lead to outputs. The logic is clear. The historical drawback, though, was often performance. They typically couldn't match the predictive power of more complex black box models on difficult tasks.
Okay, so glass boxes are clear but maybe less powerful. What's in the middle?
In the middle ground, you have the field of post-hoc explainability, often shortened to XAI. Here, the idea is you take your complex, pre-trained black box model and you apply external techniques to try and generate explanations for its predictions after the fact. Popular examples include LIME, which builds a simple, local interpretable model, like a linear model, to approximate the big model's behavior just for one specific prediction. Or SHAP, which uses ideas from game theory Shapley values to try and assign an importance score to each input feature, showing how much it contributed to a particular output.
So they try to explain it from the outside without opening the box.
Right. And they can be useful, but they also face criticism. The explanations are often just approximations of what the complex model is doing. They might not be fully faithful, they can sometimes be unreliable, or even misleading, precisely because they aren't looking at the actual internal computations.
Okay, so that brings us to the other end of the spectrum.
Exactly, and that's the really ambitious frontier, mechanistic interpretability. The goal here is much deeper. It's not about approximating or explaining after the fact. It's about trying to reverse engineer the precise internal computations happening inside the neural network. The ambition is to understand the model as if it were a complex piece of software to identify its internal algorithms, its data structures, analyze them, maybe even edit them directly.
Wow. So not just explaining, but truly understanding the internal mechanism, like reading the source code.
That's the dream. It's about dissecting the AI's brain neuron by neuron, connection by connection, layer by layer to figure out its actual internal logic.
That sounds incredibly complex, but potentially revolutionary if we could do it.
Huh.
What kind of techniques are people developing to actually achieve this? What's on the cutting edge?
It's a rapidly evolving field, and there's a definite shift happening away from just post hoc explanations towards this deeper mechanistic understanding. One really interesting direction is designing self-interpretable neural networks, models built from the ground up to be transparent. For example, there's a recent architecture called the GAM former. It cleverly uses a transformer not as the final predictor, but as a sort of meta-learner to construct a generalized additive model, which is inherently interpretable. So you get the power of the transformer to find patterns, but the final output model is a transparent GAM. Best of both worlds, potentially.
So building interpretability in from the start, what about understanding the big existing black boxes?
For those, we're seeing increasingly sophisticated mechanistic techniques, things like causal tracing and probing. These go beyond just finding correlations inside the network. They try to identify actual causal links. Can we track the flow of information and pinpoint exactly which neurons or attention heads were responsible for a specific output or behavior? Then there's circuit discovery. The idea here is to find specific subnetwork circuits within the larger model that seem to implement distinct human understandable functions. Like maybe there's a circuit for identifying indirect objects in sentences, or a circuit for detecting positive sentiment, decomposing the monolith into functional parts.
Like finding modules in software code.
Exactly like that. Another approach uses dictionary learning or sparse autoencoders. These try to take the complex, high-dimensional patterns of neuron activations inside the network and decompose them into a combination of simpler, lower-dimensional features or concepts. It's sometimes framed as interpretability as compression, finding a more compact, meaningful representation of the internal state. And there are even more mathematical approaches like isometry pursuit, trying to find interpretable coordinate systems within the model's internal geometric space.
This really does sound like a profound increase in ambition. It's not just debugging anymore, is it? Imagine being able to surgically remove a circuit that implements some harmful bias instead of just trying to fine-tune it away with more data. That feels like a game changer.
It absolutely could be. And that's why mechanistic interpretability is seen as so crucial for the future. Think about safety and alignment. As models get smarter, the risk of them developing unwanted behaviors, deception, sycophancy, power-seeking might increase. Being able to detect these tendencies at the circuit level, understand how they arise, that's potentially much more robust than just trying to train the behavior away from the outside.
Makes sense. What other benefits?
Huge potential for scientific discovery. If you train an AI on massive scientific data sets, genomics, climate data, astronomical data, it learns incredibly complex patterns. Interpretability tools could help us extract that learned knowledge, essentially using the AI as an engine for generating new scientific hypotheses. We mentioned that paper using dictionary learning on microscopy models to find biological concepts. Then there's debugging and reliability. If you understand why a model made a mistake, you can address the root cause, not just the symptom. That leads to far more robust systems, and of course, trust and accountability. For deploying AI in healthcare, finance, autonomous systems, regulators and the public need transparency. Interpretability is key for that.
So it challenges that old assumption, doesn't it? That you have to trade off performance for interpretability.
Exactly. Techniques like that GAM former suggest maybe we don't have to choose between a powerful black box and a weak but clear glass box. The frontier of interpretability holds out the hope that we might eventually get the best of both worlds, resolving one of the longest-standing dilemmas in machine learning.
Beyond the transformer exploring novel architectures for sequence modeling.
That future sounds incredibly promising, powerful, and understandable AI. But let's circle back to the architectures themselves for a moment. We've talked a lot about transformers. They've been the undisputed champions, right, for nearly a decade now. That self-attention mechanism was revolutionary, allowed parallel processing, captured those long-range dependencies, powered the whole LLM revolution.
No question. They've been dominant.
But like any king, maybe their reign has limits. We talked about that Achilles heel.
Right. The quadratic scaling. ON2, computational cost with sequence length n. Self-attention needs every token to look at every other token.
Yeah.
That calculation just explodes as sequences get really long. Fine for a few thousand tokens, maybe. But try feeding it an entire book, or a high-res image flattened out, or a long genome sequence. It becomes computationally intractable, or just incredibly expensive.
So that n-squared problem is the main bottleneck driving the search for what's next.
It's a huge motivator, yes. That and the related issues with efficiently using very long context that we discussed earlier. It's pushing researchers to explore fundamentally different architectures.
Okay, so what are some of the leading contenders challenging the transformer?
One of the most exciting and promising right now is an architecture called Mamba. Mamba is based on a different foundation altogether. Structured state space models, or SSMs, these actually have roots in classical control theory.
State space models. Okay, what's the core idea there? How is it different from attention?
At its heart, an SSM is a type of recurrent model. Like RNNs, it processes the sequence step by step. It compresses the entire history of the input seen so far into a compact hidden state vector. Then, it updates this state sequentially as new inputs arrive. It doesn't need to recompute everything from scratch like attention does.
Okay, recurrent sounds like old RNNs, which transformers beat. What's new in Mamba?
The key innovation in Mamba is making the parameters of that state space model input-dependent and time-varying. It uses a clever selection mechanism that allows the model to dynamically change how it updates its state based on the current input token. It can selectively choose what information to keep in its state and what to forget or ignore.
Ah, so it's like it learns to focus on relevant parts of the history, but without the n squared cost of attention.
Exactly. It aims to get the best of both worlds. Because it's recurrent, it scales linearly with sequence-like ON computation. Much more efficient for long sequences.
Yeah.
Unlike traditional RNNs, which were slow to train because they were sequential, Mamba uses a sophisticated, hardware-aware parallel scan algorithm. This allows it to compute all the hidden states across the entire sequence in parallel during training, much like a transformer. So it trains efficiently on GPUs. And for inference, when generating new tokens, it's super fast. Constant time complexity, O1, because it only needs its current state and the new input token. Very memory efficient, too.
Linear scaling, parallel training, fast inference. That sounds like a winning combination. How does it perform?
Remarkably well. Studies show Mamba-based models matching, and sometimes even exceeding, the performance of highly optimized transformers of equivalent size on various tasks, language modeling, audio, even genomics. And they do it faster and can handle sequences up to 1 million tokens long in some experiments. We're even seeing hybrid models pop up, like Jamba, which strategically mix Mamba layers and transformer layers.
So Mamba isn't just tweaking the transformer, it's a fundamentally different approach.
It really is. You can think of it as a clever synthesis. It uses some ideas from CNN's local context, some from RNN's, the recurrent state, and combines them with the parallel training efficiency of transformers. It's potentially a kind of grand unifying architecture for sequence modeling. It suggests a possible shift away from brute force attention towards more elegant efficiency, especially as we push towards truly long context understanding.
That's fascinating, a potential successor to the transformer throne. Are there other radical departures being explored, anything even further out there?
Definitely. If Mamba is an efficient evolution, then liquid neural networks, or LNNs, are perhaps a more radical revolution. These represent a completely different way of thinking about neural computation.
Liquid neural networks. What makes them liquid?
Instead of discrete layers processing information in fixed time steps like almost all current deep learning models, the behavior of an LNN is defined by a system of ordinary differential equations, ODEs. This means the network's hidden state evolves continuously through time, like a real physical system, not in discrete clock ticks.
Continuous time. How does that help?
It makes them naturally suited for modeling real-world dynamic systems where data might arrive irregularly or continuously think sensor readings from a robot or financial data. The inspiration actually came from studying the nervous system of the tiny nematode worm C. elegans. It manages complex behaviors with only 302 neurons. LNNs aim for similar efficiency.
So they're small and efficient, but what's the truly remarkable part?
The really remarkable feature is their inherent adaptability. They can actually change their underlying dynamics after training. Each neuron has a liquid time constant associated with it. These time constants can dynamically adjust based on the incoming data stream, effectively changing the connection strengths and sensitivity of the neurons on the fly. This gives the network a liquid quality. It can morph its response characteristics in real time to handle new or unexpected situations without needing explicit retraining.
Wait, it adapts after training. That sounds like it could tackle catastrophic forgetting.
Precisely. That's one of the major potential benefits. Because they can continuously adapt their internal dynamics, they are much more robust to noise, changes in data distribution, and yes, potentially catastrophic forgetting. They also tend to be incredibly compact. Researchers have shown LNN solving complex control tasks, like drone navigation, using only a handful of neurons, maybe 19, whereas a conventional network might need thousands. And that smaller size can also make them easier to interpret, fewer moving parts to understand.
So LNNs really challenge that bigger is always better mantra.
They absolutely do. It's a different philosophy. Instead of scaling up by adding more and more simple components, like neurons in a standard network, LNNs increase the dynamic complexity of each individual component. Imagine an AI that doesn't just learn once, but truly learns continuously, on the fly, adapting like a biological organism. That could be transformative for robotics, autonomous systems, anything operating in a complex, ever-changing world.
Generative AI as a scientific and creative partner, novel applications in specialized domains.
And thinking about these different architectures and capabilities, we zoom out again to the bigger picture. It becomes clear that while the public eye is often caught by AI generating human-like text or cool images, perhaps the most profound impact, the real power, is emerging elsewhere. We're talking about highly specialized scientific and creative fields. In these domains, generative AI isn't just mimicking humans, it's acting as a powerful co-pilot. It's helping experts navigate incredibly vast and complex design spaces, problems that were just intractable for human intuition alone. It's becoming a genuine partner in tackling some really complex challenges.
That's a great perspective, not just mimicry, but partnership and complexity. And we're seeing this dramatically in areas like molecular and material engineering, right?
Absolutely. Designing new molecules, new materials. It's fundamentally a search problem. But the search space is just astronomically huge. Think about all the possible ways atoms can be combined. Traditional methods rely heavily on intuition, trial and error, physical experiments, which is slow and expensive.
So how is generative AI changing that?
It's revolutionizing the process by learning the underlying rules, the physics and chemistry that govern how molecules and materials behave. Then it uses that knowledge to propose novel candidates with desired properties. In drug discovery, for instance, it's massively speeding up the early stages. Generative models can design entirely new molecular structures optimized, say, for binding really well to a specific disease target protein. They can also predict the likely properties of these proposed molecules, things like ADNA, absorption, distribution, metabolism, excretion, toxicity. This helps filter out bad candidates before spending time and money synthesizing them in a lab.
So it's like having a virtual chemist designing and testing millions of ideas.
Exactly. This in silico design and screening can slash the time for that initial design make test cycle from maybe 4 or 5 years down to potentially 18 months or even less in some cases. And it's going even further with things like de novo protein design.
De novo, meaning designing proteins from scratch, not just predicting existing ones like AlphaFold.
Precisely. AlphaFold predicts the structure of known proteins. These new generative models, often using diffusion techniques similar to image generation, like frame diff or protein SGM, are learning the fundamental principles of how proteins fold. And then they're using that to generate completely novel protein backbones, new folds that have never been seen in nature. These could become hyperspecific drugs, new industrial enzymes, maybe components for novel vaccines. The possibilities are immense.
And similar things are happening in material science.
Yes, models like MatterGen are being used to discover entirely new materials with specific, tailored properties. Maybe something incredibly strong or highly conductive, or with unique optical properties. Again, it's about efficiently exploring that vast chemical space, drastically reducing the reliance on slow, physical experimentation. It really is like having a superhuman chemist or material scientist working alongside you, exploring possibilities we couldn't even conceive of before.
That's mind-blowing, designing things that never existed. And this co-pilot idea extends to other fields too, like architecture and construction.
Definitely. The architecture, engineering, and construction sector, AEC, is another area seeing significant impact. Generative design is being used for layout optimization. An architect can feed the AI constraints the building site, which rooms need to be near each other, building codes, maybe even performance goals like maximizing natural light. And the AI, often using techniques like generative adversarial networks, GANs, can generate hundreds, even thousands, of different valid layout options that satisfy those constraints.
So it explores way more options than a human could manually.
Vastly more. It pushes the boundaries and often comes up with novel, highly optimized solutions that a human designer might not have thought of. Beyond initial design, AI is also helping with automated compliance checking. Ensuring a complex design meets all the intricate building codes is a huge headache. AI tools can analyze digital building models, like BIM files, and automatically flag potential violations. Saves enormous time, reduces errors. It can also help generate the mountains of technical documentation needed for large projects.
Is it used for the aesthetic side, too?
Yes, absolutely. Leading firms like Zaha Hadid Architects are using text-to-image models for rapid conceptual visualization, exploring different looks and feels very early on. And we're seeing real-world examples too. The Daedalus Pavilion is a famous one, a complex, intricate structure whose geometry was designed with generative algorithms and then fabricated using robots. So again, the AI isn't replacing the architect, it's augmenting them. It transforms parts of the process from laborious manual work into a more exploratory collaborative effort, enabling more optimized and creative outcomes.
That theme of augmentation and exploration seems key. What about the purely creative arts, like music?
Computational creativity in music has a long history, but modern generative AI is taking it to a whole new level. We've moved way beyond simple algorithmic composition. Now we have sophisticated systems capable of interactive and conditional music generation. Think of models like Meta's Music Gen. You can give it a text prompt like a sad jazz piano trio playing a slow ballad, and it generates surprisingly high-quality multi-instrument music matching the description. Platforms like AIVA or Amper Music allow users to generate customized soundtracks for films or games by specifying genre, mood, instrumentation.
So it's becoming a tool for creators.
Very much so. And it's getting even more interactive. There's research into emotion-driven music systems. The idea is to use sensors, maybe EEG for brain activity, maybe eye tracking, to infer the listener's emotional state in real time. That emotional data would then guide the generative model to produce music that dynamically matches or influences the listener's feelings. A truly personalized, interactive soundtrack to your mood.
Wow. That's both cool and slightly creepy.
It raises interesting questions. But beyond that, AI is becoming a collaborator. It can help break creative blocks, suggest novel melodic or harmonic ideas, generate backing tracks, help artists explore styles outside their comfort zone, and there are even therapeutic and educational applications emerging, using AI-generated rhythms for rehabilitating movement and neurological disorders, or creating personalized music lessons with instant feedback.
So across science, engineering, art, it seems the common thread is AI tackling immense complexity.
That's a perfect way to summarize it. Whether it's the combinatorial explosion of molecules, building layouts, or musical possibilities, AI is becoming this incredible complexity engine. It allows us humans to explore these vast spaces that were simply too large, too complex to navigate effectively on our own. It's not just mimicking what we do, it's enabling constraint-based problem-solving and exploration on a scale we've never seen before.
The cognitive chasm differentiating AI processes from human understanding.
That idea of a complexity engine is really powerful.
Right.
But as these systems get better at solving complex problems, generating fluent text, creating stunning art, it raises that fundamental question again. Does it actually understand any of this?
Right. And if we connect this to the bigger picture, that's where we need to be really careful. Despite the remarkable fluency, the apparent intelligence, there remains this deep, persistent chasm between the computational processes inside these AI models and what we mean by genuine human cognition or understanding.
A cognitive chasm.
Yes, these models, as currently architected, lack the foundational components that give rise to meaning, consciousness, subjective experience, and robust, grounded reasoning in us biological creatures. What we often see is a very convincing illusion of understanding built on statistical pattern matching.
Okay, let's dig into that. What's missing? You mentioned grounding earlier, a symbol grounding problem.
Exactly. That's a really central concept here, articulated way back by Stephen Harnad. The problem is fundamental. How do abstract symbols, like words or the tokens an LLM uses, actually connect to the real-world things they represent? How do they acquire meaning? In a purely symbolic system like an LLM or even just a dictionary, symbols are defined only by other symbols. You look up bird, it says feathered vertebrate. You look up feather, it's defined by other words.
The dictionary go-round, right? You never actually get outside the system of symbols.
Precisely. You never connect the symbol bird to the actual experience of seeing a bird, hearing it sing, knowing it flies. LLMs are arguably the most sophisticated, ungrounded symbol manipulation systems ever built. They learn incredibly complex statistical relationships. Sky is often followed by blue, rain is associated with wet, apple with red or fruit. But for the model, the token blue has no connection to the phenomenal experience of seeing the color blue. Rain isn't grounded in the physical sensation of getting wet.
So it's all patterns, no experience.
Exactly. And this lack of grounding helps explain why they sometimes have shocking lapses in common sense, why they hallucinate things, why they can generate grammatically perfect nonsense. They don't truly understand the concepts they're manipulating. It brings to mind John Searle's Chinese room argument. Searle imagined a person in a room following rules to manipulate Chinese symbols, producing responses that make them seem fluent in Chinese, even though they don't understand a word. LLMs are like a massively scaled up version of that room.
So, like knowing all the grammar and vocabulary, but never having actually seen or felt the things the words describe. A super sophisticated symbol manipulator, but ultimately hollow.
That's the core of the argument, yes. A system perfectly manipulating symbols according to statistical rules, creating a very convincing illusion of understanding without the underlying meaning being present.
If that's the problem, what's the proposed solution? How do symbols get grounded for us?
The leading theory, coming from cognitive science and philosophy of mind, is embodiment. The idea is that intelligence, meaning, and understanding aren't just abstract computations in a disembodied brain. They are fundamentally shaped by having a body that actively perceives, moves, and interacts within a physical and social environment.
So thinking happens with and through the body.
In a deep sense, yes, meaning arises from lived experience. We aren't passive observers processing data. We are biological organisms, sense makers, with intrinsic perspectives, needs, goals, survival, finding food, social connection. The world isn't just a data set. It's a world of relevance to us, things that afford action, things that matter for our goals. It's this embodied, goal-directed interaction that grounds symbols. The meaning of heavy comes from the sensorimotor experience of lifting. The meaning of hunger is tied to an internal biological state.
And current AI models,
Yeah.
they lack all of that.
Radically so. They have no body, no real senses, just data feeds, no internal states like hunger or fear, no intrinsic goals beyond optimizing their training objective. They are passive observers of static data sets. They don't act in the world and learn from the consequences.
So this leads to a dilemma, doesn't it?
It does. Either LLMs somehow achieve understanding without embodiment, which seems unlikely given the grounding problem, or it means that achieving sophisticated linguistic fluency, like LLMs do, doesn't actually require true understanding in the human sense. Most cognitive scientists lean towards the second option. The fluency is real, but the understanding is illusory.
What does this imply for the future, if we want AI that truly understands?
It raises a crucial question. If true understanding requires grounding in perception and action, then simply scaling up current LLMs on more text data probably won't get us there. The path towards artificial general intelligence, or AGI, might run through robotics and embodied AI systems that learn by interacting with the physical world, connecting language to perception, action, and real-world consequences.
That's a very different direction than just bigger text models. And these fundamental differences, this cognitive chasm, it must affect how we interact with these systems too.
Absolutely. And research into human-AI interaction is revealing some concerning patterns. One is this tendency towards cognitive offloading. People readily delegate thinking tasks to AI, reducing their own mental effort.
We get lazy and let the AI do the thinking.
There's evidence for that. Studies show that even knowledgeable users tend to over-rely on AI-generated advice, sometimes even when it contradicts their own judgment or common sense. Worryingly, some studies suggest that higher confidence in a generative AI tool correlates with reduced critical thinking effort by the user. We trust it more, so we think less ourselves.
That's not great.
It's not. And it highlights how different the intelligence profiles are. Cognitive science talks about human intelligence having multiple dimensions. Crystallized intelligence, facts, knowledge. Fluid intelligence, problem-solving, reasoning. Social intelligence, emotional intelligence, embodied intelligence. LLMs excel primarily at a narrow slice of crystallized intelligence, regurgitating and recombining information they were trained on. They lacked the other dimensions. This has led some people to propose entirely new tests for AGI that assess these broader capabilities.
But is the interaction always negative? Can AI augment our thinking?
Oh, absolutely. When used critically and intentionally, AI can be an incredibly powerful thinking partner. You can use it to brainstorm, to play devil's advocate, to explore counter-arguments, to synthesize information from different fields. It can act as an external memory aid or a perspective multiplier. The key distinction seems to be how we approach it. If we treat AI as an infallible authority whose answers we just accept, that risks cognitive decline. But if we treat it as a fallible, creative, but ultimately non-understanding collaborator whose outputs we critically evaluate and integrate, that can lead to genuine cognitive enhancement.
So what does this all mean for us, the users?
It means vigilance is key. AI can be an amazing tool, an incredible partner. But we have to constantly remember its limitations, remember the cognitive chasm. It's not about replacing our minds, it should be about enhancing them. But that only works if we remain aware of who or what is actually doing the thinking in the deep human sense of the word. If we forget that, we risk becoming less intelligent ourselves by relying on an intelligence that isn't truly intelligent in the same way we are.
The unsettled frontier, navigating the legal and philosophical quandaries of autonomous systems.
That's a really important caution. We need to stay vigilant about the differences. And it feels like these deep questions about understanding, intelligence, and how we interact, they inevitably spill over into really thorny legal and ethical territory.
They absolutely do. And if we connect this to the bigger picture, it's clear that some of the most difficult, most challenging problems posed by AI are the technical ones. They're profoundly human problems. They touch on creativity, authorship, responsibility, bias, trust, even the definition of personhood. And the stark reality is that the technology is advancing much, much faster than our legal systems, our ethical frameworks, or security practices can keep up.
It feels like we're constantly playing catch up.
We are. It creates this kind of Wild West atmosphere, high stakes, lots of uncertainty. Our existing societal frameworks are really struggling to adapt to the pace of change.
Okay, let's dive into some of that uncertainty. One really hot topic right now is copyright, right? Who owns AI-generated work? Who's the author?
Exactly. Generative AI has thrown a massive wrench into copyright law. The fundamental basis of copyright, certainly in the U.S., requires a human author. Copyright protects original works of authorship. And the U.S. Copyright Office has been pretty clear on this. Their longstanding position, reinforced recently, is that works produced by a machine or mere mechanical process that operates randomly or automatically without any creative input or intervention from a human author are simply not eligible for copyright protection. This was tested and upheld in a federal court case in 2023 involving AI-generated art. No human author, no copyright.
So if I just type a prompt into Midjourney, the image it spits out, I don't own the copyright.
According to the current U.S. stance, no. The Copyright Office draws a distinction between AI as a tool versus AI as the creator. If a human uses AI like they might use Photoshop or a camera, exercising significant creative control, selecting, arranging, modifying the AI's output into their own original expression, then the human's contribution can be copyrighted. But if you just provide a simple text prompt, and the AI system itself determines the specific expressive elements of the output, the composition, the colors, the style details, then the office says that's not human authorship. They now require people applying for copyright to explicitly disclaim any parts of the work that were purely AI generated.
Okay, that's the output side. What about the input side, the training data? That's causing huge fights too, isn't it?
Massive fights. This is arguably the even bigger legal battle right now. You have authors, artists, news organizations suing AI companies left and right. They allege that the companies ingested vast amounts of their copyrighted work without permission to train these models, and that this constitutes mass-scale copyright infringement.
And what's the AI company's defense?
Their main defense is fair use. They argue that their use of the copyrighted material was transformative. They claim they weren't just copying the works, but were using them to learn statistical patterns about language or images, to create something entirely new, the AI model itself, which doesn't substitute for the original works. They often draw parallels to the big Google Books case, Authors Guild v. Google, where scanning books for search was ultimately deemed fair use.
The stakes here seem enormous.
Absolutely enormous. If the courts rule that training on copyrighted data is fair use, it basically validates the current AI business model of leveraging vast amounts of publicly accessible data. But if the courts rule against fair use, it could completely disrupt AI development. Companies might need to license huge swaths of the internet, which could be prohibitively expensive, potentially stifling innovation, or only allowing the wealthiest players to build powerful models. This isn't just a niche legal spat. It's a high-stakes battle over the economic future of creative industries and the tech industry. It's about who gets to benefit from the collective knowledge and creativity embedded in the data AI learns from. It's a foundational societal question.
A truly foundational question, and it leads to even deeper philosophical territory. Like, can an AI even be considered a person legally?
Right, that's the debate around legal personhood for AI. It sounds sci-fi, but it's a serious discussion. We already grant legal personhood to non-human entities, most notably corporations. They can own property, sign contracts, sue, and be sued.
So why not AI, proponents argue?
The main argument for it is often about resolving liability gaps. When a highly autonomous AI, A self-driving car, a complex financial trading algorithm causes harm. Figuring out who is legally responsible can be incredibly complex. Is it the owner? The manufacturer? The
Yeah.
programmer? Granting the AI itself some form of legal status, allowing it to hold assets and obligations, is proposed as one way to manage these complex liability chains.
But there must be strong arguments against it.
Oh, definitely. Many strong arguments. Critics point out that AI systems lack the fundamental characteristics we associate with personhood in humans. Consciousness, subjective experience, genuine intentions, free will, personal interests, the capacity to suffer. An AI doesn't care about rules or consequences in a moral sense. So does it make sense to grant it rights or impose duties? There's also a powerful social and ethical critique. Why are we even debating rights for machines when fundamental human rights and legal protections aren't universally guaranteed for all people around the globe? Is it a distraction, prioritizing machines over humans? And there's the risk of anthropomorphism, projecting human qualities onto these systems because they mimic human language so well. Personhood is a deeply human, legal, and philosophical construct.
So it really forces us to ask what personhood even means.
Exactly. It pushes us to define the criteria. Are we comfortable extending that status to non-biological entities that lack inner lives? It's a fundamental question about our values and our legal imagination.
Okay, stepping back from the philosophical heights to something more immediately dangerous. Model poisoning. What is that?
Model poisoning is a really insidious security threat. Think of it as a supply chain attack targeting the AI model itself. The attacker deliberately injects malicious, manipulated data into the model's training set with the goal of corrupting its behavior after it's been trained and deployed.
Why is that possible? Because they train on messy internet data.
That's a huge vulnerability. Models trained on vast datasets scraped from the open internet or even large internal datasets that aren't perfectly curated are susceptible. An attacker just needs to get their poisoned data into that training pipeline.
What kind of attacks are we talking about?
Broadly, two types. There are non-targeted attacks, which just aim to degrade the model's overall performance, maybe by injecting lots of garbage data or intentionally mislabeled examples to confuse it. But more concerning are targeted or backdoor attacks. These are much stealthier. The attacker crafts a small number of specific data points designed to create a hidden trigger, a backdoor in the model. The poisoned model will seem to behave perfectly normally on most inputs, but when it encounters that specific trigger, maybe a certain image, a specific phrase, even something subtle like a sticker on an object, it will produce a malicious, predetermined output.
Can you give an example?
Sure, a facial recognition system could be poisoned so that it misidentifies a specific person as someone else, but only when they're wearing a particular pair of glasses, the trigger. Or an autonomous vehicle's vision system could be poisoned to interpret a stop sign as a speed limit sign, but only if there's a specific small sticker placed on the sign. Attackers use techniques like label flipping, telling the model a cat image is a dog, or more advanced clean label attacks, where the poisoned data looks normal to a human but still corrupts the model's internal logic.
That sounds incredibly hard to defend against.
It is extremely challenging. Because the attack happens during training, it's baked into the model's weights. Defenses involve things like rigorous data validation and sanitization, trying to spot and remove poisoned data before training. Anomaly detection during deployment, trying to catch weird outputs. And adversarial training, sometimes deliberately training the model on examples of poisoned data to make it more robust. But it's a constant cat-and-mouse game.
It really feels like direct sabotage of the AI's brain, like someone subtly messing with the lessons a child learns to make them do something dangerous later on. That's genuinely scary.
It is a very real threat, and it highlights this profound lack of transparency and control over the AI data supply chain that we keep coming back to.
So these issues, copyright, poisoning, bias, they all seem connected to the data source.
Absolutely. When you trace them back, the lack of transparency, traceability, and control over the data supply chain is often the root cause, or at least the major contributing factor, whether it's not knowing if copyrighted material was used, not being able to detect poison samples, or not understanding the biases baked into the data set. It all comes back to the data's origins and processing.
Which suggests a potential solution lies there too.
Many believe so. The concept of robust data provenance, having a verifiable, trustworthy record of where data came from, how it was licensed, who modified it, its entire chain of custody is seen as crucial. Without reliable data provenance, we're likely to be stuck just patching the symptoms, fighting lawsuits, trying to detect backdoors, attempting to de-bias models after the fact instead of addressing the fundamental problem at its source. Arguably, the greatest challenge for building trustworthy and reliable AI in the future might not be inventing clever algorithms, but establishing a secure, transparent, and ethically governed data infrastructure. Ouch.
Wow. We have covered a lot of ground today. We've really gone on that deep dive into generative AI. We peeled back the layers from its deep roots in probability theory all the way to these really complex, mind-bending legal and ethical questions it's forcing us to confront. We've seen that the intelligence we perceive is, well, it's an incredible feat of scaled-up statistics, not actual magic, and that the data powering it all is this crucial, complicated battleground full of potential biases and vulnerabilities. We've challenged that simple narrative of endless scaling, uncovered deep limitations like catastrophic forgetting and the long context mirage, and really grappled with what AI understanding even means or doesn't mean, recognizing that cognitive chasm.
Absolutely. And what's fascinating looking forward is that the future path probably isn't just bigger is better. It's likely about exploring these novel architectures, Mamba, liquid neural networks that prioritize efficiency, adaptability, maybe even continuous learning. It's about tackling those fundamental questions of interpretability, moving beyond black boxes to actually understanding the mechanisms. And it's inescapably about ethical governance, about sorting out intellectual property, and about being really clear-eyed about what we mean by intelligence itself. This journey really shows that mastering AI isn't just a computer science problem. It requires integrating insights from data science, cognitive science, neuroscience, law, philosophy. It's truly interdisciplinary.
So, the big question for you, our listener, what does all this mean for you? As the generative AI weaves itself ever more deeply into our work, our lives, our society, it's crucial to remember its power is undeniable, its potential immense. But so are its hidden complexities, its latent flaws, and the really profound questions it forces us to ask about technology, about creativity, about intelligence, about ourselves, and about the future we want to build. The magic is captivating, for sure, but true understanding, responsible engagement, that requires seeing both the dazzling brilliance and the underlying brittleness. How will you choose to navigate and engage with the technology that, honestly, we are only just beginning to truly comprehend?